All right, so we were in the middle of figuring out how to answer the membership question for in general. So as we summarized last time, let's go through and talk about CYK kind of from the beginning. We had a string that we want to determine if it's in a particular language. In order to do this, the grammar has to be in Chomsky normal form. So conversion into Chomsky normal form is the first thing that has to happen. That is the two rules. We have a non-terminal arrow, non-terminal, non-terminal, or non-terminal arrow terminal. Those are the only two possible rule types that can be used in Chomsky normal form. We break the string down into its associated characters and then one index those so that we can define substrings of this in terms of Wij. I is where the substring begins, J is where it ends, inclusive. So unlike the substring method in Java, then we are trying to answer the question, which non-terminals can produce this string directly? And we care about answering that just for the start non-terminal. If the start non-terminal is in this set of productions that can produce this string, then we say, yes, this string can be produced by the language represented by this grammar. And if it's not, then we can't. So we break it down and we're going to answer this via dynamic programming. For the couple people who weren't here yesterday, who's vastly familiar with dynamic programming? So you know what it is and how to apply it?
Wasn't algorithms are required for this class?
Yes, that does not mean that people have an understanding of dynamic programming. I have historically found, but
Okay.
if you've talked about it and you're familiar with it and have seen examples of it, yesterday I broke down a kind of a Fibonacci sequence from a top-down perspective. So Fibonacci of 7 is Fibonacci of 6 plus Fibonacci of 5, and then you continue that tree down and you find that you're redoing a lot of work in those computations. If you build it from the bottom up and store them in a table, then when you look it up, it turns an exponentially complex problem because for each tree, each level of that is going to have twice as many nodes as the prior one. Then you end up with a linear time if you go bottom up, storing them, you calculate Fibonacci of 1, store it, Fibonacci of 2, store it, Fibonacci of 3, store it. And that way that tree turns into just a linked list with a friend. So it turns an exponential complexity problem down into a linear complexity problem and makes it much easier. So a version of this with just one extra dimension is going to be this problem. As we're going to go through CYK and using another triangular diagonal table, we're going to fill that in from the ground up. So to do that, I was using this example. So the table for this is scale up there at the end. We need you. We had 1, 2, 3, 4, 5. I care about the length of this string as the number of cells on the first row, and then it's going to be diagonal from there. I think my table yesterday was pretty good. Oh well, we'll make do. And each of the components from this represents n1, 1, n2, 2, n3, 3, n4, 4, and n5, 5. This is n1, 2, and this is n4, 5, n1, 3, n3, 5, n1, 4, n4, 5, and n1, 5, where the final answer is going to be. So that's the cell we end up caring about. And this is how you're going to make any associated CYK table. So substrings of length 1, substrings of length 2, 3, 4, 5. This is the substring that is the first character, second character, third character, last character. Substring that is the first 2 characters, second and third, third and fourth, fourth and fifth. Substring that is positions 1, 2, and 3, 2, 3, and 4, 3, 4, and 5, etc. So it's every possible substring of this string. That's what each cell is going to represent. And what we want to write in each of these cells is a set of all possible left-hand sides that can produce the associated right-hand sides that can produce that substring. So the first row is far and away the easiest to fill in because they are just lookups into the grammar. We're going to bring down this first substring, this A, and we're going to say what left-hand sides can produce A directly from a right-hand side. And the answer is just A. The capital A can produce this lowercase a through that. So what goes here is the set that contains A. And that is it. Same thing for N22, except now we're looking at the second A. So what can produce just an A from the right-hand side, and it's the set that contains A. For this, we're looking at the third character. We're looking for the left-hand side of everything that can produce on the right-hand side a lowercase b, which is just the production B. And we'll see that that continues throughout the rest of the table. And we have a first row. As we go up a row, every time we do, it gets a little bit harder. So now we have to figure out for the substring here that is AA, starting at some left-hand side, how can we produce that AA? Is that possible to do in some capacity? So to do that, it's going to be lookups into part of the table that we have completed so far. So I like to think of bringing down this AA here, and then thinking about what are all of the possible ways to divide this in half, or divide this in chunks so that there's a left-hand side and a right-hand side. If we do that in this way, then we can create a left-hand side and a right-hand side. The left-hand side is a lookup to the substring 1,1, and the right-hand side is a lookup to the substring 2,2. And we have answers for all of that in the table. So we're going to bring down this set that contains A, and this set that contains A, and we're going to take the cross product of those two sets, which generates a list of tuples, where the first element comes from an element of the first set, the second element comes from an element of the second set. So we get the tuple that contains AA as the only tuple that can produce this. So what we're going to do is we're going to now concatenate these together and look for them on the right-hand side of a production here. Is there any right-hand side that contains AA? The answer is no. S can't make it, A can't make it, B can't make it. So because of this, there is actually no way to produce this substring from starting at any possible non-terminal in the grammar. Interesting. Questions so far? All right, we move on to N23, which is going to be the substring starting at position 2 and going up to and including position 3. So we get rid of that, we extend that to there. This is our AB. The entirety of the second row, there's only going to be one place where we can break this string somewhere in the middle, such that we have a left-hand side and a right-hand side. So we do that. And this is a lookup to N22. This is a lookup to N33. We look at N22, we get an A. N33, we have a B. Take that cross product, we get the tuple AB. Anything that can produce AB on the right-hand side?
Just B.
B can.
O and S.
And S can, yes. So this becomes the set that contains both S and B. Great. We have that cell filled out. We do exactly the same thing, except now we're going to look at the next substring, looking at B and B. This is a lookup to N33 and N44. So this creates B and B, which gives us the tuple BB. Anything that can make BB? Yes, A. roughly this is gonna be exactly the same because it's the exact same substring, and if we look into the table, 3, 3, 4, 4, the cross product of those sets is gonna be the exact same as the cross product of those two sets. So I'll save myself just a little bit of work and just throw the A in here. Duplicating was here to there. Does it make sense why I'm able to make that shortcut and do that? Because this substring BB is the same as that substring BB, which producing that B made the same sets down here. So looking at the cross product of this and this is going to be the exact same as the cross product between this and this. Which means that we're also going to be looking for BB on the right-hand side, which is going to be the exact same set of productions that could produce BB the first time. So let's try to save myself just a little bit of work, because it gets a little more complicated as we work our way up. Things on the floor. Moving up a row, moving up in complexity. Now we're going to add another bit of complexity to this. When we have AAB as our substring, so now we're looking at that. There are multiple places that we could break this in the middle to where there's a left-hand side and a right-hand side. It does not actually have to be in the middle. It could be anywhere such that there is a non-empty left-hand side and a non-empty right-hand side. So I'm going to draw this out twice. And we can break this in the middle here and break this in the middle here, which creates both two different, what I'm going to call trees, but the associated lookups in this table are now substrings that we have solved. Do we agree that these are all substrings on the left-hand side or right-hand side of something that exists in the table somewhere? So rather than recalculate it like we would have to if we weren't using dynamic programming and storing things in a table, we're going to actually look them up. This A is N11. This AB is the substring starting at position 2, ending at position 3, which is right there. That's this cell, S and B. So this was A. This was S and B. Looking here, this AA is N12, which is that cell right there. What's the empty set cross anything?
Empty set.
Empty set. So we have, I'm going to write this just to be sure that we see it the first time, N12 cross N33. But we have empty set cross, and at this point we can just kind of stop because the result of this is going to be the empty set. We just stop caring about this whole tree. Can't produce anything of value. What are the possible tuples that can come from this first side?
A and S or A and B.
Yeah, so we're going to have AS, AB. So now we're looking for either of these there. So what would happen if we had something here is we would union it with what's over here. This would be kind of this set union some other set, but this set is going to be the empty set because of the fact that that was not possible. So we're looking for either AS or AB somewhere in there. Where are all the left-hand non-terminals that can produce either AS or AB? S and B, yeah, so both, nothing can produce AS. S and B can produce AB. So what goes in this cell is S and B. Does it make sense why? All right, now we've thought about every possible breakdown of the substring AAB. So we can restart with the next cell. So ignore the first character, add in the next character, we have ABB. I'm just going to write ABB so that we can split here and split here. This A is no longer 1, 1, it's 2, 2. So I'm going to stop writing the N now because it's annoying. And the BB is 3, 4. This AB is 2, 3, and BB is 4, 4. These become lookups into our table. So 2, 2 is right there. That's an A. 3, 4. 1, 2, 2, 3, 3, 4 is also an A. 2, 3 is S and B. 4, 4 is just B. So making our tuples, if we actually wanted to fully write this out now, I'll do it because we have both sides. We would get A as a set. We're going to union that with everything we can make on the right-hand side, which is a tuple containing S and B, and a tuple containing B and B. Make sense why? Anyone with questions on how we got that? So now we're looking for anything on the right-hand side that can produce AA or SB or BB. What is the set of all left-hand sides that can produce any of those? Just A? Yeah, nothing produces AA, nothing produces SB, and only A produces BB. So what goes in this cell is A. A lot of work to write one thing in one cell of this table. It just gets worse. It's a good thing the string is so short. All right, last cell on this row, we're moving this A, making a B. We have BBB or BBB. But there's still a distinction here between where this gets split. This is 3, 3 and 4, 5. This is 3, 4 and 5, 5. So if we look at 3, 3, we get B. If we look at 4, 5, we get A. If we look at 3, 4, we get A. And if we look at 5, 5, we get B. So we get the tuple BA, that set, union the set with the tuple AB. That is a gross A. Anything that produces BA or AB on the other side?
B produces AB.
And
S produces AB.
yes. So this is going to be the set containing both S and B. Excellent. Now we have all of the information we need to answer all the queries in the next row. So up we go. So now we're looking at substrings of length 4. There are fewer of them, but they're more complicated. So we're going to look at AABB. And how many times should I write this on the board now?
2, what, sorry.
How many possible midpoints are there for a 4-character string?
3.
3? Yeah. So we're going to write AABB, AABB, and AABB. We're going to split this after the first character, after the second character, and after the third character. Breaking this down, we end up with 1, 1, and 2, 4. We end up with 1, 2, and 3, 4. And we end up with 1, 3, and 4, 4 as our possible substrings, breaking that in any possible middle point. So 1, 1 is a lookup, giving us A. 2, 4 is a lookup, 1, 3, 2, 4, that gives us A. 1, 2 is a lookup, gives us empty, so we stop caring. 1, 3 gives us a lookup that's S and B. 4, 4 gives us a lookup that is B. So we're going to have AA, SB, or BB. What can produce any of those?
A can produce BB.
A can produce BB. That's what goes here. Notice how I stopped caring about showing quite as much work, because if I did that, that's all we do today. It still is gonna be close to all we do today. And this is a small example.
I cannot imagine doing this for like a larger string and a more complex grammar where it's just entire chalkboard gets filled up with random scribbles.
You can't imagine, but you will be able to imagine when you do it on your homework. How to ruin someone's day. The best and worst parts of this job. You can just say one thing in a kind of tone of voice, and then someone's just like, no, you've ruined my day. Can split here, can split here, can split here. So now we're dealing with the substring from 2 up to 5. So this is 2, 2, and 3, 5. This is 2, 3, and 4, 5. This is 2, 4, and 5, 5. Not even drawing the arrows for the trees anymore. 2, 2 is a lookup to A. 3, 5 is a lookup to S and B. 2, 3 is a lookup to S and B. 4, 5 is a lookup to A. 2, 4 is a lookup to A. And 5, 5 is a lookup to B. Oh boy. All right, we have AS, AB, SA, BA, and AB. What is the union of all of the left-hand sides that can produce that?
The one that you're going to use is AB because you can have S or B produce it.
Yep. Anything from AS? No. Anything from SA? No. Anything from BA? No. Anything from AB? We already asked that question. It's a duplicate question. We can't add it multiple times to a set of left-hand symbols. So it is just S and B. Now for the final fun part. We're gonna look at the entire substring. How many times should I write it? 4 times. A, B, 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 A, B, 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 A, B, 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 A, B, B, B. Just make me a computer already. So we can split here, 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 or here, giving us 1, 1, and 2, 5, 1, 2, and 3, 5, 1, 3, and 4, 5, and 1, 4, and 5, 5. I think I did that right. 1, 1 is A. 2, 5 is S and B. 1, 2 is empty. I'm gonna stop thinking about it. 1, 3 is S and B. 4, 5 is A. 1, 4 is A. And 5, 5 is B. What's nice about this is once we reach this final cell, we actually don't have to worry about filling it completely. We're just looking for one thing. Is S anywhere in this set? And that means we're looking for AB somewhere, and AB can either come from here or here. Once you do that, you know that S is in this set. So really all you care about is putting a check mark here, that S is in this set. And the conclusion that we can draw is that this grammar can produce the string AABBB via some sequence of productions. And actually that some sequence can be reconstructed by going down and figuring out exactly how this is done. So we're going to break the string down into its components, the A and the ABBB. This A says that there is something that can generate immediately that first symbol. So that A comes from this A, and everything else is going to come from that be in some capacity. And since it's not a single character, we choose something that we know exactly which production to apply. And then we can recurse, try to figure out the ABBB problem, which is demonstrated here that we can get from there from S and B, which we know from here. So we know to select the AB from there, breaking that down. It allows you to really see where that came from. And if you stored exactly that, you can reconstruct the path. Usually that's unnecessary. Just answering the membership question is enough for CYK. How are we doing? Questions on that process? That was a very long process.
You said the process is called CYK. What does it stand for? You?
It's the author's initials, or the three authors' first initials of their last names. I forget what they are. This, I mentioned last time, is also your first programming project. So in case you weren't paying enough attention, you will be implementing this as well in a general case. But this to me is a very fun programming project because you can throw very large strings and very complicated grammars at this and it spits out an answer very quickly because this is a cubic time function. The worst case for the number of columns here is just the size of the string. So this is the size of W. How big are the columns? The rows, sorry. This is also the length of W. And what is the worst case for the amount of work that we have to do to figure this out? It is based on, breaking this down into, at worst, the length of W minus 1 strings. And there are fewer than that unless you're in the last row. So it really becomes an upper bound, which is why we say that this algorithm is in big O of n cubed. It's actually a little bit better than that, but we have a dimension here, a dimension here, and a dimension here, all of which are based on the size of the length of the string, just the length of the string. But this is a perfectly fine runtime for reasonably sized strings and reasonably sized grammars. As soon as it gets extremely complex, it'd be great if we had something faster than this. And it turns out in special cases, we do have something faster than this, and we will come back and talk about that. That's the very last thing we do in this class. Because it is not particularly easy, but once you see the big picture, it makes it make a lot more sense. And a combination of this and that are what compilers do for the membership problem. To be able to say something like, when you write a program, is that program syntactically correct? If we take the Java grammar that I showed you in the first week, and you write some Java program, it's exactly the same thing as saying, here are all the statements and all the tokens in each of those statements. If we can tokenize your program, feed it into a grammar, this Java grammar, as just a sequence of the tokens that make up your program, can the Java grammar generate this program? If so, then it's legal and syntactically correct. If it can't, then it is not. Questions on CYK? Anything else I can explain? Do you feel like you'd be able to implement something like this on a homework?
Take me like an hour, but I could. I'm just waiting for it to be a series of questions through like A through D, and it's like do all of these.
You know me so well.
No, but it's so much fun.
All right, I think then if you have further questions, we can go over some examples in office hours or you can look back over the lecture and watch me reconstruct this solution. If you're already in the future, looking back on this from the future, you can look back at it again. Recursion, infinite timeline. All right, so this is just the rest of the work that we did. I throw as much as I can on the slide so that you can refer to it in the slide without having to go back to the entire lecture video, but this is just the work that we did. In exquisite detail. We did all of that work. We talked about the complexity. There it is in slide form. Woohoo. All right. We can move on to more exciting things. We finally get to talk about context-free language automata. This is very exciting. So I mentioned yesterday that we started from the regular language. We started in on automata first, state machines, and then we talked about regular expressions and grammars. And it was because it was really easy to visualize and to think about regular languages in terms of a state machine representation. It turns out that that is a little bit less true in context-free languages. It's actually slightly simpler to think about the grammar representation, which is why I tried to introduce that first. But just like with regular languages, you can utilize the concept of a state machine. The question is just, how do we relax the restrictions, or what do we need to change to represent this same class of language with some kind of state machine? What's one thing we've noticed about the context-free languages that we have seen so far that was not true of regular languages? What was the main restriction on regular languages?
If we're talking of them in terms of grammar, we had to represent them either right facing or left facing, which means that each character would have had to be differentiable for each one, and then to be able to do it in a minimal amount of space. So
Yeah.
you can't just have infinite
Yeah,
space for
finite memory
Yeah.
is the really big restriction on regular languages. And context-free languages can actually store infinite memory. And we need to be able to represent a language like A to the N, B to the N, which we proved wasn't regular via the context-free pumping lemma, and then the regular pumping lemma. Then we showed that it was context-free by making a context-free grammar for it. But A to the N, B to the N needs an infinite amount of memory because we don't know how many A's are coming. There's no limit to those number of A's, and we need to be able to count those number of A's so that when we see an associated number of B's, we can say there were the same number of B's as the A's that I've already seen. So we need a state machine to be able to have infinite memory. How are we going to be able to represent that? So we've done all of this. Looking at A to the N, B to the N, we know it's not regular. There's no maximum to the number of A's that can come before B's. We just know that it is some finite amount, but there's no limit to that finite amount. You can't have A to the infinity, B to the infinity. Haha, I fooled you. That's not a string because it doesn't terminate. But you say I have an automata, a regular language automata, the DFA, that has 16 million states. And I say, all right, can it represent A to the 30 million, B to the 30 million? You go, dang, I need to add more states. There's always a counter to that. I had fun writing this slide. I do remember infinite power or something of the sort running through my mind as I wrote infinite in all caps. But let's get an idea now of what a push-down automata actually looks like. And yes, we're going to use the acronym PDA, and yes, it stands for push-down automata, not that other thing. So PDA, exactly like a non-deterministic finite automata, except that now it's going to carry with it an additional data structure. So in each state, when you're in that state, there is also an infinitely sized stack that is floating around with you as you do this. And you can do exactly what you can do to a stack, to this stack. You can push, you can pop, and you can peek. Look at the top value and not actually remove it. So familiarity with stacks, we remember everything about stacks from data structures and the hopefully 10 plus times you've used them since then. So we do need to define a stack alphabet and a stack start symbol, because the characters that we use for the stack do not have to be the same characters that we read from the input. We can utilize our own stack language and have that represent something based on the actual language of what we are seeing. So here is what we're going to call an NPDA, a non-deterministic pushdown acceptor or automata. Exactly like the DFA, instead of just having an input file and a control unit, we now have an infinite stack that it can read from and write to as it reads through the input file. And it turns out that this single change allows us to map onto all context-free languages. This is all we need to be able to come up with a state machine representation. But it means that it is a little bit trickier to write the actual state machines, and some of the state machines actually look kind of gross, because a lot of the transitions are going to be just manipulating the stack and not doing other things, or manipulating the stack and reading an input symbol, but staying in the same state. So they end up looking kind of weird and not quite as puzzle friendly as the DFAs and NFAs that we've seen so far, which is why I introduced them after grammars. So the differences between the DFA NFA that you'd seen before is that we have now a stack alphabet, and the transition function is now not just a state and an input symbol to another state, but it's now a state and an input symbol and a top of stack symbol to a new state. So we care about what's on top of the stack, and that becomes an additional dimension that we can use when we decide how we're going to transition between states. That will make much more sense, I think, with an example. So I actually did just talk about this. Rather than transitioning from a state to another state, consuming an input character, then we also need to make an associated change to the stack. This can be a push, a pop, or a no-op, where you don't do anything to that top of stack symbol, which is why it's partially why it's non-deterministic. The other non-deterministic is that you can do different things to the stack on the same input symbol. So push, pop, or what we're going to define as a no-op. If the stack is empty, then we can't do anything. So we need to at least be able to read that bottom of stack symbol. So there's a bottom of stack symbol that's separate from the rest of the alphabet that says you've reached the bottom of the stack. If you try to pop from an empty stack, that's just a straight error. So we cannot have that happen at all. We also know that the range of the transition function has to be finite, which means that the number of possible strings that we can push to or pop from the stack has to also be finite. Here is what a transition would look like in an NPDA. This says we're transitioning from state Q1. We read an A from the input, and there is a B on top of the stack. If all three of those things are true, then we can either enter the state Q2 and push CD onto the stack, or we can enter Q3 and have popped the B that was on top of the stack. So when you read a character from the top of the stack, you actually are popping it. If you want to do a no-op, you have to pop and then push that same character back. So if we saw Q3 comma B there, that would be the equivalent of a no-op. So we automatically assume that we are popping when we do it. There's quite a bit on this slide. Does anyone have any questions so far? I think an example will clear up most of it, but anything that I can clear up at this point? All right. Here is a sequence of transitions. It defines the set of states up top, Q0 through Q3. The input alphabet, which is AB, the stack alphabet, which is 0, 1. So it's a different alphabet between what we're reading in the string and what we're using in the stack. The bottom of stack character is going to be, I think, 0. I don't know if I love that. I think it needs to be a Z. And then the final state is Q3. Z is typically used as our bottom of stack character. It just works nicely because it doesn't really represent anything else. Then we state initial state is Q0, and here are the associated transitions. So just like in an NFA, we don't necessarily have to represent every single possible transition. So what this does, we can see that this adds a 1 to the stack when an A is read. So when we read an A and there's a 0 on the stack, we are going to push back that 0 and push a 1 on top of that. So you read this string from right to left and push the characters on from right to left. You're reading it from top down. Or if we're in state Q3, then we pop the 0. Note that this is just saying we popped the 0, we put it back on, but we pushed an additional 1. So the equivalent between this transition is just pushing a 1 when we read an A from state Q0. From Q0, if there is nothing in the input string, there's a 0 on the stack, then we can transition to Q3, popping off that 0. If we're in state Q1, we read an A, there's a 1 on the stack, then we are going to pop that 1, push it back. So that's the equivalent of a no-op, and push an extra 1. So reading these rules in tandem allows us to see that a 1 is added to whatever is on the stack whenever we read an A. That's kind of a logical conclusion from looking at these two transitions. It removes a 1 from the stack when a B is read. So we see a B here. If there's a 1 on the stack and we're in state Q1, then we pop that 1. If there's a 1 on the stack and we're in state Q2, we pop that 1. Between those two transition definitions, it tells us that whenever there's a 1 on the stack and we're in those states, we're going to remove it. It transitions from Q1 to Q2 after the last A is read. Note that we can read A's from state Q0 and state Q1, but we cannot read A's from state Q2 or Q3. We can't read B's from state Q0, but we can read B's in state Q1 or Q2. So this tells us we're reading some A's, putting some 1s on the stack. Then we are reading some B's and taking some 1s off the stack. What is this doing?
Is it going to count the number of A's to make sure there's the same number of B's?
Yes. This is going to be an NPDA for A to the N, B to the N. If we were going to draw this out, it would look something like this. So edges are no longer just a single character like they were in DFAs and NFAs. They are triples. Tuples with 3 elements. So each state looks exactly as it did before, but every edge has 3 components. The character that is read from the input, what is popped off the stack, and what is pushed on the stack. And you do it in that order. You pop before you push.
And this works like an NFA. So if I have a B on the stack during Q0, then the
Instant fail.
instant fail.
Yep, instantly reject. Exactly. So let's run through exactly what this would do or look like with the last couple minutes on some A to the N, B to the N example, and something that doesn't adhere to that. So give me some string that adheres to A to the N, B to the N, and it's not longer than, let's say, 6 characters.
A, B, B.
Great. So if we input A, B, B, to this, then what we're going to do is we're going to keep track of a stack kind of on the side, as well as where we are. So we started in Q0, and the pointer for this is on the first character. So what we know about the state is that we see an A, and it did say that the bottom of stack character is a 0, which is kind of annoying. I'm actually going to add one to this that says a Z 1Z. And this allows us to make a transition on an empty stack character that's not 0, because I don't like that. I'll need another one for Q3 to be able to say they should be lambda Z lambda here instead of 0, and lambda Z lambda for that. I just prefer having a separate bottom of stack character from one that we're actively considering to be binary or something that is binary. The 0 would represent just something, we're going to be adding ones and removing ones, so it is okay for that 0 to be there. But for the rest of this class, we're usually using Z as that bottom of stack character, so I just want to get us used to it. So wherever we see a 0, really just, I guess, replace that with it. All right, so now if there is a Z on the bottom of stack, this really just becomes that, so we don't need that anymore. Let's read that A, pop the Z, push from right to left. So we're going to push the Z right back on, and then push a 1 on top of that. As we do that, we read this A, so we're going to move this arrow 1 position to the right, and we're going to move from Q0 to Q1. So now we are currently in Q1. We see another A. This tells us if we see an A and there is a 1 on top of the stack, which there is, then we should pop that 1 and push 1, 1. We move our string pointer 1 place to the right, and we transition from Q1 back to Q1. We now see a B with a 1 on top of the stack. So we're able to see that we are reading a B with a 1 on top of the stack. This says, consume that B, pop a 1, and push nothing. So it's the equivalent of a pop. We do that, we transition from Q1 to Q2, and we move our string pointer 1 space to the right. From Q2, if we read a B, and there's a 1 on top of the stack, we're going to pop that 1. We're going to move our stack pointer to be pointing past the end of the string. We are looping back around to Q2. And now we see that we have our pointing at nothing with a bottom of stack character on top of the stack. So we are going to pop off that bottom of stack character as we do it and move over to Q3. If we have an empty stack, including without that bottom of stack character, and we are in a final state, and the string pointer is past the end of the string, then we accept. But all of those need to be true in order to accept. So we're in a final state, we've finished parsing the string, and depending on how you design this, I'll give you 2 options. You can either have the bottom, have an empty stack, or have the bottom of stack character on the stack. And the only thing that would change is you would push this Z right back on. If you do that, as long as you stay consistent with this meaning of I accept either when the bottom of stack character is the only character on the stack, or if it's empty. Both of those are fine, as long as you're consistent.
For starting with P0 and A, how do you know to go to Q1 instead of Q3?
Because using non-determinism, we'll end up going both places. And if this is AABB, you are absolutely right that what we could have done when the pointer was here is CAZ, pop that off the stack, so the Z is gone. We consumed the A, we're in state Q3. Can we accept?
Technically,
We can't, because we're not at the end of the string. That's one of the things that has to be true even if we have that bottom of the stack character, or if the stack is empty, if we're not at the end of the string, even if we're in an accepting state, we cannot accept. And since from that state Q3, there's nothing to do on an A, there's no defined transition, we instantly fail. So this creates two threads from Q0. One of those threads fails instantly, the other one continues and eventually accepts. So since there is a thread that accepts, just like with an NFA, then we accept the whole thing.
Wouldn't it also accept just A then, in that case, because you'd be taken to the final state and there's no other characters to use?
Yeah, so you would have to, in this case, do something that keeps the bottom of the stack character on or pushes something, because I don't think. Honestly, the only reason that I would do this, I think this is actually a mistake in the book, is the only reason you should transition from Q0 to Q3 is on empty. You should not be able to do that on an A. But you're allowed to do this in general because of non-determinism. It's not allowed in a deterministic pushdown automata, though, which we'll talk about later. Questions on that? We're a couple minutes over, so we'll end class here and come back to it next week. There is a homework that has actually been published now, so get started on that early. The TA does not have office hours on Monday, but I do. Note that there are pumping lemmas in this homework. And that is one of the hardest things that you will do in this class to understand. So please get started early and come see me if there's anything that I can do to help you do better on that assignment. It'll be a challenge, but I am here for you. Please make use of my office hours. Otherwise, I cry in my office alone, and that's not a pretty sight.
Don't worry, I'll at least be there with you.